Hello dear students, welcome to mathematics class. In this class, let us discuss the theorem on Riemann integrable function. So here it is the statement, if f belongs to R of closed interval AB, means if f is a Riemann integrable function on the closed interval AB, then f square belongs to R of closed interval AB, means if f is the Riemann integrable function, then f square is also Riemann integrable function. So therefore it is the statement of the theorem. Let us prove this one. Proof: since f belongs to R of closed interval AB, means if since f is a Riemann integrable function, then it implies that f is bounded on the same interval AB. If f is Riemann integrable function, then f is bounded. So by the definition of bounded function, therefore there exists k greater than 0 such that mod f of x less than or equal to k for all x belongs to the closed interval AB. So here by the definition of the bounded function, there exists k which is a positive real number such that mod f of x, means the value of the function f for all the x in the interval AB is either less than or equal to that k, which is the positive real number. And now mod f square of x, this can be written as mod f of x into mod f of x, because mod x square is equal to mod x into mod x, or mod xy is equal to mod x into mod y, means modulus of the product of two functions or two variables is equal to the product of modulus functions x and y. So similarly, mod f square of x can be written as mod f of x into f of x. So therefore this is equal to mod f of x into mod f of x. And here we know that mod f of x is less than or equal to k. So therefore this is less than or equal to k into k. Since mod f of x is less than k, here also less than k, and it is a product of these two. So therefore this one is less than k into k, which is equal to k square. So therefore mod f square of x is less than or equal to k square. So here since k is greater than 0, k square is also greater than 0, and k is a real number, k square is also real. So therefore k square is greater than 0 and it is the real number. So again, by using the definition of the bounded function, we can say that mod f of square is less than or equal to k square, means f square is a bounded function. F square is a bounded function. Here if f is bounded, then we have proved that f square is also a bounded function on the same interval. Now since f is R integrable on closed interval AB, now for given epsilon greater than 0, there exists a partition P of closed interval AB such that, so by using the necessary and sufficient condition for Riemann integrability, we can say that if f is Riemann integrable, then for given epsilon greater than 0, there exists a partition P of closed interval AB such that upper sum, that is UPF, minus lower sum is less than epsilon, and consider this as equation 1. So, here it is the condition for integrability. So, already f is Riemann integrable, then this condition must be true. So, therefore, here epsilon greater than 0 and P is the partition satisfying the condition that upper sum minus lower sum of the function f is less than epsilon, where epsilon is any arbitrary constant. Now, let small mr, capital Mr and small mr dash, capital Mr dash be the infimum and supremum of f square and f respectively on the rth subinterval xr minus 1 to xr, which can be denoted as IR. So, here small mr, capital Mr and mr dash, capital Mr dash be the infimum and supremum of f square. So, here this mr is the infimum of f square, capital Mr is the supremum of f square and mr dash is the infimum of f, capital Mr dash is the supremum of f on the rth subinterval, which is given by xr minus 1 to xr and denoted as IR. Then let us consider the two arbitrary points. Let alpha comma beta belongs to IR, where IR is xr minus 1 to xr. Alpha comma beta belongs to IR. B arbitrary points, such that. So, here these are the 2 points, any points in the rth subintervals, such that f square of alpha is equal to capital Mr and f square of beta is small mr. Means at the point alpha, the value of the function is equal to supremum of that one, and at the point beta, value of the function f square is equal to infimum, and f of alpha is capital Mr dash and f of beta is small mr dash. So, these are the supremum and infimum at the points alpha and beta respectively. Now, consider mod of f square alpha minus f square beta, mod of f square alpha minus f square beta. So, here this is equal to mod of, it is similar to the identity that a square minus b square, that is equal to a plus b into a minus b. So, therefore, this can be written as f of alpha plus f of beta into f of alpha minus f of beta. So, here a square minus b square, that is a plus b into a minus b, and this is equal to, now separating the mod of these two products, that is mod of f of alpha plus f of beta into f of alpha minus f of beta. So, here this one is less than or equal to, we know that mod of x plus y is less than or equal to mod x plus mod y. So, therefore, here mod of x plus y is there, means f of alpha plus f of beta. So, this one is less than or equal to f of alpha plus f of beta into mod of f of alpha minus f of beta, this one as it is, and here mod f of alpha mod f of beta, and this is less than or equal to. So, already we know that mod f of x is less than or equal to k for all x belongs to the closed interval a b, right. So here alpha and beta are also the points of the closed interval AB only, because these two are the points in Rth subinterval, and Rth subinterval means that is the part of the closed interval AB. So therefore this alpha and beta are also the points of the closed interval AB. Hence f of alpha is less than or equal to k, f of beta is also less than or equal to k. So therefore k plus k becomes 2k into mod f of alpha minus f of beta, and this is less than or equal to, here this can be written as 2k into, here f of alpha is mr dash minus small mr dash. So therefore mod of f square alpha minus f square beta, here f of alpha is supremum and f of beta is infimum. So therefore this f square alpha minus f square beta is less than or equal to 2k into mr dash minus mr dash, and let us consider this one as the second equation. Now here if f is a bounded function, if f is a bounded function with the bounds small m and capital M defined on closed interval AB, then the oscillation means the difference of upper and lower bound, that is capital M minus small m of f on the closed interval AB is the supremum of the set mod of f of x minus f of y such that x comma y belongs to the closed interval AB. So this is one property of the bounded function. So here f is a bounded function with the bounds small m and capital M defined on some closed interval AB, then the oscillation of the function is given by upper bound minus lower bound of the function f on the same interval AB, then this oscillation is the supremum of the set. This becomes the supremum of the set mod f of x minus f of y, where x and y are the points of the closed interval AB. Now we are going to use the same property for f square, for the function f square. Now since f square is bounded on the closed interval AB with the supremum capital MR and infimum small mr on the rth subinterval IR. Here that AB is any interval, so here we are considering the rth subinterval. Then we can write that mod f square of alpha minus f square of beta is less than or equal to mr minus mr. So here just compare these two statements. Here f square is bounded, here f is bounded on the AB, but here the interval is IR, that is from XR minus 1 to XR, and the supremum and infimum of the function of R, small m and capital M, here capital MR and small mr. Then this oscillation, that is m minus m, is the supremum of the function, supremum of the set, this one mod f of x minus f of y. Supremum means that is the upper bound, so therefore that must be greater of all the elements of this set. So therefore here mr minus mr is the supremum of the set f square minus alpha minus f square minus f square beta, right. So therefore here this quantity must be always less than or equal to the oscillation of the function f square, that is mr minus mr. So therefore by using this statement we have written the result as f square minus alpha minus f square beta, that f square alpha minus f square beta, right. So since it is the supremum, this must be greater than all the elements of this set, that f square alpha minus f square beta. Then next, also since f is bounded, on the closed interval a b, because already f is Riemann integrable, so therefore f is bounded, and supremum of f is capital mr dash and infimum of f is small mr dash on the rth subinterval. Then now apply the same statement for the function f. Then here we can write mod f of alpha minus f of beta is less than or equal to mr dash minus mr dash. So there the previous step, here we have applied that f square is bounded on AB and this mr and small mr are the supremum and infimum of the function f square on IR. Then this is our result. Here f is bounded on AB and supremum of f is capital mr dash and infimum of f is small mr dash on IR. Then this is the result. These two are depending on this statement, that oscillation is the supremum of the set mod f of x minus f of y. Now from equation 2 we can say that 2k into capital mr dash minus small mr dash is an upper bound of mod f square alpha minus f square beta it implies mr minus mr is less than 2k mr dash minus mr dash. So here in equation 2, so this is the second equation. In this equation we have written that mod f square alpha minus f square beta is less than or equal to 2k times mr dash minus mr dash. So this is greater value, means it is the upper bound of the function f square alpha minus f square beta. But here this mr minus mr, that is the supremum of the same function. Supremum means least upper bound. So it is also a upper bound, this one is also upper bound, but in these two upper bounds this one is the least upper bound, that is the supremum. So supremum means this must be less than this quantity. So therefore here we have written that mr minus mr less than or equal to 2k times mr dash minus mr dash. Now consider UPF square minus LPF square is equal upper sum of the function f square on the partition P and lower sum of the function f square on the partition P is equal to, by using the formula summation over r is equal to 1 to n, upper sum means we need to consider the supremum. So, supremum of f square, that is mr into delta r, minus summation over r is equal to 1 to n small mr into delta r, and this can be written in simplified form as summation over r is equal to 1 to n capital Mr minus small mr into delta r, because summation is in common and delta r is also the common quantity. So, therefore, this can be written like this. Now, from let us consider this as equation number 3. So, from equation 3, this quantity mr minus mr is less than the 2k times mr dash minus mr dash. So, therefore, this is less than or equal to summation over r is equal to 1 to n 2k mr dash minus mr dash into delta r. So, this is by using from the third equation, and this is less than or equal to. Now, multiplying separately, the 2k is constant value, let us write this as outside of the summation. Then summation over r is equal to 1 to n capital mr dash into delta r, we are multiplying. Then summation over r is equal to 1 to n small mr dash into delta r. This is less than or equal to 2k. So, here summation over r is equal to 1 capital mr dash into delta r, where capital mr dash is the supremum of the function f. So, therefore, this summation is the upper sum, that is u p f, minus here small mr dash is the infimum of the function f, hence it is the lower sum of the function f, LPF. Now, we know that UPF minus LPF is less than epsilon, that is 2k into epsilon, that is from 1. In the first equation, that UPF minus LPF is less than epsilon, that we have considered. So, therefore, here 2k is some constant value, epsilon is also some arbitrary constant which is greater than 0. So, therefore, this total is also some constant. So, therefore, UPF square minus LPF square is less than, let us consider this product 2k into epsilon as the new constant, that is epsilon dash. So, therefore, by using necessary and sufficient condition for Riemann integrability, what we can write here, UPF minus LPF is less than epsilon means f is Riemann integrable. So, here UPF square minus LPF square is less than epsilon dash, where epsilon dash is, here you can write, where epsilon dash is arbitrary. It is also some arbitrary constant. Since it is also less than epsilon dash, it implies f square belongs to R of closed interval AB. So, therefore, our theorem proved. In the statement it is given that if f is Riemann integrable function, then f square is also Riemann integrable function. So, therefore, here f square is also Riemann integrable function, that we have proved by using the necessary and sufficient condition for R integrability.